Okay. All right, were folks able to successfully get to PrairieTest and sign up? Good. Okay, definitely sign up for one of those. Sorry, it's right over lecture time. Sorry for the late notice. First time doing this. If you can't make any of the times definitively, you can't move around your schedule. We might be able to add some times later, but it's not guaranteed. So if you can make something, sign up. If you can't make anything, you can let us know and we can see if we can do something, but it's not 100% certain. Okay, today we're going to talk about sampling. I really like this lecture. I say this for every lecture, but I do really like this lecture. Um, cool topic. I think it can sound like a boring topic to start off, or kind of like visualization, where you like assume it's this easy thing you don't have to think very hard about, but like secretly, silently, it's actually a pretty complex thing, and there's a lot of fun nuance. So a couple announcements before we get started. Lab due tonight, homework also due tonight. We're moving quickly. Homework 3 is long. It's interesting though. You're going to work with text of New York Times articles. It's pretty cool, and it's super recent articles, last 5-ish years or so. Start that early. Do Wednesday, July 9th. And then, like I had the announcement up before, orientation quiz signups are live now. SDH 200, Sutarja Dai Hall, today and tomorrow. It's highly recommended. It's not required, but highly recommend you go see what it's like to take an exam in there. Keep in mind, you're in a comfy chair instead of a lecture seat. You've got a big desk instead of a little desk. There's some nice stuff to it. You can wear headphones during the exam, but they have to be the headphones that are there. Any questions about that for folks, I guess, who are here in person about the orientation quiz or sort of the computerized testing? I'll give more opportunities to ask about this, but if there are any questions now, I'm happy to take some of them. Yes. Good question. They're provided computers there. They're locked down. They don't access the internet. It's just like a keyboard and standard entry. Yeah. Other questions about computerized testing? Yes. Oh, I mean, you can show up for whatever. It's just kind of questions that are asking you about the protocols and logistics. It's not graded or anything like that. It's just so you can get a sense of what it's like to answer questions and remind yourself what sort of the policies are if you like miss your exam slot or something like this. Yeah. Other questions? Yes, Brian. If you need to use scratch paper, I think we'll be able to provide blank sheets. You just can't take it with you. Yeah, but there won't be any sort of questions that you answer on written paper and then submit that written answer. It's just scratch paper for your own benefit. But we're not going to ask questions that like necessarily require like deep scratch paper, right? But if you want to use it, you probably can. Yeah. What else? Yes. You'll see at the orientation quiz that there is a digitized reference sheet. It's not necessarily the reference sheet you're going to see the day of the exam, but it's very similar. Yeah. What else? What else? It's definitely like a new thing. Keep in mind when you take like your GRE, computerized testing. Did you all do standardized testing growing up on computers? Yeah, so no, mostly paper all over the place. I don't know. They were like starting to switch to computerized when I was in school, and then they switched back. And anyway, I know like the ACT and SAT are kind of moving in this direction. So there's like benefits to this that we can discuss maybe offline. Come to office hours and we can talk more about the decision and how it benefits you, how it benefits the instructors, how it just like makes learning better, because sometimes it can be hard to see that. Anyway, before. Last time we were talking about exploring the data, opening up the data, visualizing the data, using pandas to look around. Now we're going to talk a little bit about how you get data and like the pitfalls of getting data. We don't spend a lot of time in Data 100 on actually getting the data, even though I've mentioned before, this is like often the hardest part about data science, and you spend the most time on actually getting the data. But you'll get a little bit of a taste of it today and how to get data in a good way. Okay, so roadmap. Let's start with censuses and surveys, just some terminology for us to understand. So a census is a complete count or survey of a population. I'm interested in understanding how voters will vote in an election in 6 months. The population is everyone who will vote at the election, right? If I could ask everybody how they're going to vote and they were all honest, I wouldn't need statistics per se. I'd have my answer, right? I'd have my answer right there. So a census is literally asking everybody. And this is really expensive and hard to do. Every individual is included. The population is everybody you're trying to study. So it doesn't necessarily just have to be people. It can be like bacteria in your gut, right? If you want to understand what like the flora look like in somebody's gut, you're going to have to take like a biopsy or a small sample. You can think of all of the bacteria as the population, or trees of a certain species we'll see in a little bit. Same idea. Doesn't have to be people. So what is the census? When you hear the census, which is data that people use all the time in data science projects, typically it's referring to the US decennial census. This is constitutionally mandated. This isn't something that was decided later on. In the Constitution, it was said that we need to do a census every 10 years, and we still do it. Last one was in 2020. It was very difficult during COVID. It attempts to count every person, but sort of notoriously, it's essentially impossible to do that. So interesting things you can get with the census, though. Census data is fantastic. It's all public. You can go online, download it. I use it for projects all the time. But there's lots of interesting patterns you can see from it. So on the left here, we have population change, where blue is a reduction in population, red is growth. You can see Florida is getting a lot of people, Mississippi Delta is losing a lot of people. But the place I want you to sort of focus on is California. So this was the 10 years, 2010 to 2020. We can see there was slight growth in like the Bay Area, right? Slight growth. But then in 2020 to 2023, the color scheme sort of flips here. So now red represents a loss. You'll notice that the Bay Area is red on the right. And suddenly there's a ton of people leaving, and you hear they're all moving where? A lot of people are going to like Idaho. Idaho is growing like crazy as a state. Lots of super interesting things from the census without even joining to other data. You can stare at these plots all day and find very, very interesting patterns. But notice this was between 2020 and 2023. The left was 2010 to 2020. That's census data. How did we get 2023 data? Another good term to just be familiar with if you need data from a between year is something called the ACS, the American Community Survey. It's done every 1, 3, and 5 years. It's a sample, not a census, just a sample. And so there's error bars and sort of everything in the ACS because we're not sampling every single person in the population. We're not doing a census. Okay, so what does a census actually look like? What does the sort of surveying actually look like? You can take a whole course at Berkeley on surveying, but here's what like a census form looks like that they try to get every single person in the United States to fill out. You may not have filled one out, your family may have filled one out on your behalf, but you can see there's all kinds of information that's being asked. And people don't always fill out information that's sent to them over the mail, so there's like literally census takers that go out door to door. You may have seen one. You may know somebody who's volunteered or signed up to be a census taker. You can see this person's going right to someone's door and asking who lives there. This isn't just like a couple people. If you look at the actual graph of the number of federal workers in the United States year by year, you see all those jumps? They're huge jumps. That's just census workers. This is like a huge part of the federal workforce every 10 years. So this census is like a massive, massive undertaking. This is not an easy thing. So I'm just trying to say all this to convince you of why we need sampling, right? We don't necessarily have the resources to do this very frequently. We just don't. We just don't. Okay, so what is sampling? Censuses are expensive and difficult. A sample is some subset of a population. You could have a random sample. Typically, when we say a sample in Data 100, if we don't specify what kind of sample it is or describe it, often people are referring to some kind of random sample, but we could have a non-random sample as well. And then two other terms you should know. So sampling versus inference. We're going to see inference later on in Data 100. Inference is this idea of taking some information from a sample and saying something meaningful about a population. So these are also like terms you should just sort of have in your statistical lexicon as a data scientist when you're talking about analyses. The population is ultimately what we're trying to say something about. Who are all of the possible people who might buy your product, who are out there, versus who actually ends up buying your product or who you're actually able to talk to. Sampling is the idea of getting a sample from a population. Inference is the idea of saying something meaningful about a population from a sample. Okay, and we don't spend a ton of time on either of these in Data 100. We're gonna have a couple lectures on inference and then this lecture on sampling. This is a huge part of statistics and data science, okay? All right, so case study. Let me give you something to sort of sink your teeth into. Love this case study. It's a classic one, and we're going to extend it sort of further than maybe if you've seen it before. So in 1936, there was a presidential election. It was the second time Roosevelt was running. Okay, so everybody knew Roosevelt was doing pretty good job from 1932. And he ran against a person named Alf Landon. So there was Roosevelt, a Democrat, running against Alf Landon, a Republican. And we know that Roosevelt ended up winning, and he ended up winning 2 more terms, the longest serving president in the United States history, right? But ahead of this election, there were these election polls that were conducted to try to figure out who would actually win this election. And so we all know now Roosevelt won. But what did the polls say? So a pretty amazing thing happened. This group called Literary Digest that no longer exists. In 1936, pre-computer, right? Pre-computer, they had successfully predicted the presidential outcomes in the last 5 elections, and so they were going to just keep going and do it for this one too by asking their readers. And so they sent a survey to 10 million people. Keep in mind, there's like no computers here, right? They have like printing presses, so you can send out, like 10 million postcards. And they get contact information not just from Literary Digest readers, that's part of it, but they look at phone books, they look at the actual subscribers to their magazine, they look at automobile registrations like through the DMV. When somebody registers their car, they put a name and phone number in. And they contact all these people and they try to figure out how they voted. And just keep in mind, 10 million people without computers is an unbelievable undertaking. The amount of brute force to do this is crazy. Absolutely crazy. So they get a sample of 10 million people, and what do they see? They see that 43% indicate that they're going to vote for Roosevelt. Okay, 43% indicate that they're going to vote for Roosevelt. So that Roosevelt would lose, right? Roosevelt would lose. In the actual election, it was one of the biggest landslides in American history. I think it was the biggest electoral landslide in history. Roosevelt won with 61%. Okay. So what happened? And this is the sort of standard story if you've seen this before. What happened? Well, phone books, Literary Digest subscribers, and automobile registrants, especially in 1936, maybe when everybody doesn't have a car, maybe aren't representative of the actual voters in the country, right? So a really big sample size is not going to fix your bad sampling method. This is like one of the first lessons to take out. If there's bias in the way that you sample, and someone suggests, well, just sample more people, a larger sample size doesn't fix bias. It does good things, but it doesn't fix bias. If you have an error in one direction, it's going to keep that error, even if you have this unbelievably large sample size. I cannot stress how crazy it is how many people they had here. And so what happened? Ultimately, the sample wasn't representative of the population. The sampled voters are able to subscribe to magazines in 1936. They have a car in 1936. They have a phone. They tended to be more affluent and more Republican in that time. And then also, they sent out 10 million postcards, but only 2.4 million people got back, which is really high. 24% response rate nowadays is like unbelievably high. But again, like they were tabulating 2.4 million of these postcards by hand to figure out how people would vote. What do we think about the other 76% of people? If you're too busy to fill out the survey, that might be associated with voting for Roosevelt, let's say, if you have less time, right? Someone who's just sitting around at home might be more likely to vote Republican. So we have 2 problems here, right? We have a representativeness problem, distinct problems. Representativeness problem, the people who we asked in the first place, and then we also have a non-response problem. We don't know how people would have filled out the survey. Later analyses seem to suggest that non-response was the bigger problem in the survey. Non-response was the bigger problem. Okay, so then this guy, George Gallup, comes along. You may have heard of Gallup polls. New York Times, Siena, Gallup, these are like words that are sometimes thrown around towards elections when they poll to try to figure out who's going to win. So George Gallup comes around in 1936, and George Gallup surveys a much, much smaller group, 50,000 people, still a lot. You actually don't even need 50,000 people to get this question correct. So George Gallup surveys a much smaller sample size, but he does it in a different way. It's more representative, and George Gallup's poll predicts 56% for Roosevelt. So still an under prediction, but a lot better. Okay, and so a better sample will serve you a lot better than a bigger bad sample. But this is often where the story ends, and we're going to come back to this story a little bit later in the lecture. Could the Literary Digest have done any better with the data they had? Was it possible for them to get closer to that 61% with their sample? Did they do anything wrong, or were they not clever enough, or did something happen where they could have actually had a better answer? So that's what we're going to get to. That's the sort of extension of this story that we're going to see towards the end of today. But for now, the story to take away, the best way. So this slide in the past said the easiest way. It's not the easiest way. The best way to get a representative sample is through randomization. If you can randomize, that gives you lots of benefits in statistics. You get representativeness, In causal inference, you can start making causal claims like in an experiment. Randomization is sort of like the secret sauce here. If you can get it, you're in business. Okay, it's very, very important to try to get it if you can. But just keep in mind, I like to mention, like, it's not always easy or possible to get randomization. So I don't want you thinking that if we're not randomized, you're totally lost. If you have a non-random survey where you're asking customers and whoever gets back to you responds, it's a non-random sample, can you just not use that data? What are you actually supposed to do if you have a non-random sample? So we'll get to that a little later. Okay, but to start, we're going to sort of start thinking about inference in a setting where, and sampling in a setting where we're able to randomly sample. Okay. All right, so sampling errors. What are the different kinds of errors? We saw two before, where our sample wasn't representative and our sample was filled with a lot of people who only could respond, right? We had a lot of people who didn't respond to the survey. What are these sort of formally called? So the first error you should be familiar with, the big vocab lecture, the first one is called variance formally, or what we'll refer to as chance error. Variance or chance error. So random samples can vary from what you might expect in either direction. So if we sample some population, we might undercount some value, we might overcount some value just because of randomness. In the 100 people we sample, we might end up with people that look a little different than the population in either direction. Okay, that's called chance error. What's one way to reduce chance error? So the chance error you can reduce by increasing your sample size. If you want to make your sample look more and more like the population, increase the size of your sample. Why does that work? If I keep increasing the size of my sample, eventually I'm just getting the entire population and there is no error. There is no chance error. I have my answer. So increasing the sample size will help. Stratifying will also help. That's a new thing we're going to talk about later in this lecture. Okay. Here's a visual for you. We might have a population filled with people. We have two different kinds of people in this particular case. The best way to think about this, if I take a small random sample versus a large random sample, there's a larger probability that in the small random sample, I'm going to be unlucky. If I have a smaller random sample, it's more likely that my sample won't look like the population. I'm more likely to get just an unlucky sample. As I take a larger and larger sample, I'm more and more guaranteed for my sample to look like the actual population. This is the idea of chance error. If we have a small random sample, we're going to have larger errors that can go in either direction. We're just not going to look as representative. If we grow our sample, we're going to look more representative. Keep in mind this error can go in both directions, undercounting or overcounting. So that's chance error. And then we have stuff called bias. We have bias. So there's chance error or variance that can go in either direction. These are terms that are going to come back to haunt you later in the class outside of the context of sampling too. So chance error or variance can go in either direction. Bias is always in one direction. It can be negative, it can be positive. It's a systematic error in one direction. Systematic error in one direction. And there's lots of different kinds of biases. Lots of different kinds of biases. Tons of Wikipedia pages about all these subtypes of biases. A super interesting rabbit hole to go down. People have spent a lot of time trying to make surveys work. We're going to talk about a couple of them here. So the common biases. First one is called selection bias. We're going to do selection bias. We're going to do response bias. And then we're going to do non-response bias. But we'll start with selection bias. So selection bias is when you have bias in the way that you select individuals for your sample. So what do I mean by this? You're systematically excluding particular groups from your sample. If I use DMV phone books to identify people for my survey, who gets excluded? People who don't drive? Anybody else? People who don't have cars or people who don't, if it's DMV phone books, people who don't have phones, right? So you have to think about these things when you're sampling. So selection bias, nice example. Literary Digest excluded people who weren't in phone books. They don't have phones, okay? They don't have cars if they got those phone books from the DMV. Some more terminology for you to think about. Here's our population of interest, or our population, all voters. Here's where Literary Digest went and looked. None of this is drawn to scale. This is like a metaphor here. But we can imagine that this dotted frame here, the sampling frame, of the Literary Digest is everyone who could have been sampled by the Literary Digest. Notice that there is overlap with the actual population of voters. They did get some voters, but they also may have gotten people who weren't actually going to vote, who ended up responding. Some people who read Literary Digest maybe didn't end up voting. Right? So notice there's sort of missing overlap between the sampling frame and the population, and then in the actual sample, you can see again, we don't have perfect overlap with our population of interest. Okay, so we have our population, everybody who that we're interested in studying. We have our sampling frame, everybody who could be sampled, and we have our actual sample, who actually got sampled at the end. There's that second step of the sampling frame that people often forget. They think that we're sampling directly from the population, when in fact we may be sampling only from a portion of the population and even a little bit beyond the population. We may be a little bit over inclusive of people. And so what did George Gallup do better? George Gallup did a random sample. What's the point of a random sample? We're going to try to take that sampling frame and make it overlap more with our population. That's the gold standard. We want to be sampling directly from the population if we can. We want to improve the overlap of the sampling frame and the population so that our sample does a better job of representing the population. Okay, so reducing selection bias is synonymous with increasing the overlap of the sampling frame and the population. Those two ideas are synonymous with one another, the same idea. Okay, other kinds of biases to talk about. Response bias, also called measurement bias. You should be familiar with both terms. So response bias or measurement bias is when you have a problem with how people are able to respond, who want to respond, and how you are measuring responses. Same idea here. So what do I mean by this? Miscalibrated survey questions. The way you ask questions is giving you a systematically different answer than what you were looking for. What you are measuring is different than what you actually want to measure. Obvious example here. Will you vote for Roosevelt or Landon? If you say Roosevelt, I'll give you $1. Is someone going to give you the honest answer there? No, right? They're more likely to say Roosevelt because they want the $1. And so if you claim that your survey is measuring who people are going to vote for, you have response bias or measurement bias. Okay, you have to claim what you actually are trying to measure and then state what you are actually measuring. Here's a more subtle example. Do you agree or disagree with the statement, I will vote for Roosevelt? Agree or disagree statements can be a little bit tricky to work with in surveys because people tend to be agreeing. People tend to like to agree. We have this sort of bias to want to agree with whoever is surveying us. So you want to be very, very, very careful with questions about agree or disagree. And so how do you avoid response bias or measurement bias? You make better questions and you iterate on your survey over and over and over again and really think through how people could respond in different ways to your surveys. I have tons of links, again, to Wikipedia pages of all the different kinds of response biases that are out there. Lots of very interesting research. And then finally, non-response bias. This one is somewhat straightforward. It's just people who respond look different than people who didn't respond to your survey. This was the biggest problem in the Literary Digest poll. In the Literary Digest poll, only about a quarter of people actually responded. 75% didn't respond. Those 75% might look different than those 25%. And later analyses seem to indicate that that was the case. Okay, so we're building up our big vocabulary here so that we can get the grand finale here of fixing the Literary Digest poll. Okay, so we got measurement bias, response bias, non-response bias, and selection bias. Where do we go from here? And then how do you fix non-response bias? You essentially just need to make people respond more. Lots of ways to do this. You can incentivize completion, but you have to do it in a smart way. Again, asking people, here's $1 if you vote, and if you vote for Roosevelt, I'll give you maybe an extra $1. That's not a good way to incentivize completion. Okay, so what do we do in our classes to get increased participation on evaluations? Often we'll give a half point of extra credit for people who fill out evaluations, another half point if the entire class reaches like a 90% threshold. Right? Does that bias responses positively? Maybe. I don't know. If people who really want the extra credit are more likely not to like the class, we don't know. Right? Reducing the number and length of questions is a classic. Undergrads, when they send out surveys, often send surveys that are way too long and way too unclear. Very common. It's a skill. Hard to get right. People don't want to read your survey. Just always assume that. Make your survey as short as possible. Okay, convenience samples. Another nice term to know. So these are very, very common. These are common. What is a convenience sample? It's essentially a sample that is convenient for us to access. It's a non-random. It's non-random. Okay, if I wanted to figure out how people were feeling about data 100 and I surveyed everybody in this room coming to lecture, that would be a convenience sample. It would be a biased sample. All of you probably feel differently about data 100 than the course does as a whole, right? If you're willing to show up to lecture, you probably feel different about data 100 than necessarily the course as a whole. Maybe that's different in the summer than in the fall or the spring, I don't know, but that would ultimately be a convenience sample. It's just people I have access to, okay? Here's an example from somebody who used to teach the class a while back. They were an ecologist. They were studying different eucalyptus trees in New South Wales, Australia. They had a sort of library of eucalyptus trees that had been measured already. And they were interested in mapping the geographic distribution of eucalyptus trees across the country. Here are the maps on the right. So in the top right, we can see the uncorrected map. So this library of eucalyptus trees was based in Sydney. And you can see that most of the eucalyptus trees that they found were close to Sydney. They were convenient. They were easy to get access to. But this is a little bit of a hint for what's coming here in the bottom right. You can correct surveys for bias. So bias isn't insurmountable. Bias isn't insurmountable. The best thing you can do is correct it ahead of time, but sometimes we can't, and sometimes we have to correct bias after the fact. That's something we're going to see in a little bit. And we can see in the bottom right, once it's corrected for bias, using some methods we're going to talk about and some more advanced methods, there's a more natural distribution of eucalyptus trees around Sydney. But just keep in mind, a convenience sample suffers from selection bias. Suffers from selection bias. This is a non-representative group of the entire Data 100 class, most likely. Okay. Also, I have a link there for you if you want to check it out. We're really bad as humans at mimicking randomness. If we claim that we can try to randomize something just sort of by eyeballing it, we are absolutely awful at it. We're also really awful at distinguishing between pictures that were sort of drawn randomly versus not. So they'll have people look at like pictures of like dots or like stars in the sky. You can kind of imagine and look at like different plots of these stars and talk which one of these was distributed totally randomly by like a random number generator, which of these was distributed according to some pattern. People are terrible at identifying which ones are actually random. So don't trust yourself when it comes to identifying randomness. Trust your code. All right, so some types of sampling, and then we're going to get into a Slido here. At the end, I think we're going to have time to do a demo as well. How are we doing on time? We're pretty good. Okay, so types of sampling. Probability samples. Lots of terminology today. Probability samples. So if we know the probability that a particular observation will get sampled, it's a probability sample. It's a probability sample. This is technically a random sample. Now, important terminology here. If someone says that they conducted a random sample, they usually mean that they conducted a simple random sample or a stratified sample. Even though a probability sample is technically a random sample, where you can't predict with exactitude who's going to get selected, usually when someone says random sample, this is not what they're referring to. So let's say I have 3 TAs, Alan, Ben, and Celine, and I want to sample 2 of them. Alan is always selected. There's a 100% chance that you select Alan. Okay, that is a probability. And then we flip a coin to pick Ben or Celine. This isn't a very great sampling strategy, but it is technically a random sample, and it is a probability sample because I can assign a probability to every possible grouping. The probability of selecting Alan and Ben is 50%. Alan and Celine is 50%. The probability of selecting both Ben and Celine and not Alan is 0. If I can assign a probability to every possible grouping, that is a probability sample, and technically a random sample. But again, when we say random sample in the real world, we're usually not referring to this kind of sampling. We're referring to something called simple random sampling. What is a simple random sample? So if you hear simple random sample, think of a raffle, think of putting names in a hat, think of a random number generator. It's sort of the most natural way that you might think about sampling. You assign everybody a number, you randomly pick numbers with equal probability. That's a simple random sample. Every individual has an equally likely chance of being selected. We select people without replacement. You can't be selected more than once. You can't be selected more than once. It's drawn uniformly at random. Uniformly means everybody has exactly the same probability of being drawn. The trickier thing is this subset idea, that every subset of individuals has the same chance of being selected. What do I mean by subset? That means that if I were to ask you what's the probability of drawing person 5 and person 11, and I was sampling pairs of people, that needs to be the same as the probability of selecting person 9 and person 27. So not only does every individual have the same probability of being selected, every group of any size has the same probability of being selected. That's the trickier part of a simple random sample. Okay, so every individual has the same chance, every pair has the same chance, every triple has the same chance as any other triple. We're going to practice with this in just a second. Okay, and try to identify whether something is actually a simple random sample. So let me give you a sampling scheme to work with, and then we will discuss. So let's say we have a class roster with 1,200 students. So typical Data 100 in the fall or spring has about 1,200 people in it. Summer, you're lucky, we got 150, 160. You get more attention, okay? But typically there are 1,200 students in Data 100 and about 50 teaching staff. So let's say we pick one of the first 10 students on our roster list. Okay, we're gonna pick one of the first 10. So let's say I pick student 7. And then what I'm going to do is pick every 10th student after that. So let's say I pick 7, I'm going to pick 17, 27, 37. I'm going to go all the way down until I've cleared out the list. Okay, so this is my proposed sampling scheme for you all. Here's a picture of it. Randomly select somebody in the first 10. Let's say we pick number 3. We're going to pick the 10th person after that, 10th person after that, and so on. 3 questions for you to do on Slido. Is this a probability sample? Does each person have the same probability of being selected? Okay. And is this a simple random sample? 3 distinct questions. Is this a probability sample? Does each person have the same probability of being selected? And is this a simple random sample? Let's start with the first one. Let's start with the first one. Feel free, talk with your neighbors. This is a good discussion question since there's no work. No need to whisper. Go ahead. Hey, let's try this one. I'm hiding in the back. Can you take this and just pass it around, or just take one, pass it down? Thank you. Okay, is this a probability sample? Oh, my clicker doesn't work. Let's see. Is this a probability sample? Yes, it is. Yes, this is a probability sample. Why is this a probability sample? We can assign a probability to every possible grouping here. We can assign a probability. There's 10 possible samples. I can pick any one of the first 10 people, and then I pick every 10th person after that. So when I start out, I can only pick one of 10 people, and then the sample is essentially deterministic after that point. So there's 10 possible samples that I could collect. Each one of those samples has an equal probability. Any other grouping has a probability of 0. Those are probabilities. This is a probability sample. This is technically a random sample. This is technically a random sample. Next question. Does each student have the same probability of being selected? Does each student have the same probability of being selected? Okay, why don't you throw in an answer? Does each student have the same probability of being selected here? So I'm going to randomly select one of the first 10 students, and then after that, I'm going to choose every 10th person. So there's 10 distinct samples. Each one of those samples doesn't share any students. Each of those samples has a 10% probability of being selected. So every student has a 10% probability of being selected because they are only in one of those samples, and all of those samples are equally likely. So yes, each student has the same probability of being selected. Let me go through that reasoning one more time. That's not really reasoning. So we have 10 students at the very front of the line. Each one of them has an equal probability of being selected. That was the first part. We're going to select every 10th student after that. And so that ends up creating 10 distinct samples. Those are 10 distinct samples of students that have no overlap. They have no overlap with one another. Any given student is in one of those samples, and each sample is equally likely. So there's a 1 in 10 chance. All right, the kicker. Is this a simple random sample? Is this a simple random sample based on the definitions we've talked about so far? Give this one a try. And if folks have questions, I can also come around to clarify. Okay, is this a simple random sample? All right, here's the kicker. Like I said, sampling on the surface, what do you know? Random sample, good. That's kind of like one of the important things to take out of today, but it can be a little tricky. Is this a simple random sample? We're pretty split. We're pretty split. This is not a simple random sample. A simple random sample is a sample where every individual and group has an equally likely chance of being selected. Every student has a 1 in 10 chance of being selected. What's the probability of selecting the second student and the third student in a sample? Is it possible? Not possible. What's the probability of selecting the first student and the 11th student? They will always be in a sample together, 1 in 10 chance. Okay? So any pair has either a 1 in 10 chance of being selected together or a 0 chance of being selected together. This is not a simple random sample. This is not a simple random sample. Okay? All right, so these are good to study to really deeply understand what these terms mean. Let's keep going. I think we're at a break. Let's take 2 minutes. If you got questions, feel free to raise your hand. I can come around. Reminder for anybody who came a little late, make sure to go to PrairieTest.com to sign up for an orientation quiz at the computer-based testing facility if you haven't already. PrairieTest.com, there's an extra I after A, P-R-A-I-R-I-E test.com. I've gotten very good at spelling prairie over the last couple weeks. And if you're having trouble signing up for an orientation quiz, you got to let us know ASAP because there's an issue with you on the roster. Okay, second half of today, we're going to talk about some other sampling schemes, really just one other sampling scheme that's very important for you to know for industry, for academia, just life in general, because it's essentially strictly better than a simple random sample. You don't always need it, but it's essentially strictly better. It's either as good or better than a simple random sample. And then we're going to use that sampling scheme and actually work backwards to go correct the literary digest poll, or see if we can actually go correct the literary digest poll. Okay, so let's say I want to interview a representative sample of 12 students in Data 100. And keep in mind, this is Data 100 during the school year. So I have 1,200 students in the class, and I want to get a just representative sample of 12. Let's say I want to conduct an extensive interview. Each interview is a half hour. I only have 6 hours to spare. I want to try to get 12 student opinions that are pretty representative. So each semester during the school year, there's usually 100 graduate students in Data 100. They sign up for the class as Data 200 or Data 200S. And then the remaining 1,100 are undergraduates. So what I'm going to do is I'm going to conduct a simple random sample in SRS on one of the 100 grad students. So I'm going to get the email addresses of all 100 grad students. So my sampling frame is the same as the population, right? That's great. Unusual. And I'm going to randomly sample one of those graduate students. And let's say they have to get back to me if I email them. Okay, so I'm going to randomly sample one grad student, and then I'm going to conduct a simple random sample with 11 of the 1,100 undergrads. So 1% of each group, right? Here's a picture. Enrolled students, we have 1,200 of them. 100 are grad students. I'm going to sample one. 1,100 are undergrads. I'm going to sample 11 of them. And again, here I'm writing sampled. I mean randomly sampled. This is a common thing when people say sampled or randomly sampled. If they don't sort of define what they're talking about, they're usually referring to a simple random sample. And if they say sample, they're usually talking about a random sample. But always clarify with people. My question for you, is this legit? Does every student have the same probability of being selected for an interview in this sampling scheme that I'm proposing to you? Talk with your neighbor. And you can assume we're separately conducting a simple random sample on each of these groups. Separately conducting an SRS on each of these two groups. So do this step by step. Start with the grad students. What's the probability that any individual grad student is selected? Then do it for undergrads. So if I have 100 grad students and I randomly sample one, each grad student has a 1% chance of being selected. If I have 1,100 undergrads and I randomly sample 11 of them, each undergrad has an 11 over 1,100 chance of being selected, which reduces down to 1 over 100, also a 1% chance of being selected. So every student does have the same chance of being selected here, assuming we're conducting a simple random sample on each group. Okay, assuming we're conducting a simple random sample on each group. If it's not a simple random sample, everything sort of goes out the window, right? Okay, so my question for you is this. Is this still useful in any way? Like why would we do this? Yeah, why would we do this? Is there any reason to do this versus a simple random sample? Can you think of any reason to do this or not? Or not? Give this one a try. Feel free to throw up a word here. Is there a reason to do this or not? Can you think of any reason why? Okay, seeing a lot of good things. I'll leave this up so you can put in an answer, but it seems like some words are sort of already sticking out here. This idea of ensuring at least one grad student is represented. All of you care a lot about grad students. That's really nice. So out of 1,200 students, 100 are grad students. And by randomly sampling one graduate student, by saying ahead of time, we are picking one graduate student, we are guaranteeing that at least one graduate student voice is heard. If we didn't do this, maybe we would have sampled none. Maybe we would have sampled two. Maybe we would have sampled all 100 in some universe. Not 100, excuse me, we're sampling 12. Maybe we would have sampled 12. Maybe we would have sampled 12 of them, right? And gotten really sort of unlucky and kind of a weird sample. And so not only are we ensuring representation, we're preventing overrepresentation, right? We're not just ensuring that they're not underrepresented, we're also ensuring they're not overrepresented, right? We're sort of constraining to be representative, okay? So there is a benefit here. We have guaranteed proportional representation of undergrads and graduate students. Everybody is getting represented to the same extent that they exist in the population. There's a big assumption underlying all this, and that is that I actually know what the population looks like. If I don't know what the population looks like, I can't really do this. I knew ahead of time that 100 out of 1,200 were grad students. If I was sampling from some population, but I didn't know the composition, I can't stratify. That's what this is called. I can't conduct a stratified random sample. Ultimately, in terms of the vocab we've talked about so far, what does this mean? What we've done is reduced chance error. So not only can you reduce chance error by increasing your sample size and making your sample look more like the population, you can reduce chance error by stratifying your sample. We're ensuring that there's representation in our sample compared to our population. That's a reduction in chance error. Doesn't send it to zero, right? We can still have different grad students that are sampled each time, but now we're not going to get these weird cases where there are no grad students or 2 or 3 or 12, right? So this is called stratified random sampling. The plural of stratum is strata. Each of these groups we just created in the population are called strata. Each one individually is a stratum, just like we saw data and datum. No one actually says datum. No one actually says stratum. Everyone just says strata, even if they're referring to a singular term. But this is stratified random sampling. In this case, we have 2 strata, grad students and undergrads. Strata describe the population, and then we sample from those strata. So what is stratified random sampling? We take our sampling frame, which in this case is the same as the population. Someone brought up a good point last time. It's the same as the population in this case. We take our sampling frame, we divide it into non-overlapping strata. They can't be overlapping, based on some characteristic. In this case, it was just one characteristic, grad versus undergrad. We could have had 2. We could have had 2-dimensional strata here. We could have had grad students and undergrads, and something like major or like master's degree or degree type, maybe like STEM, non-STEM, something like this, right? Then what do we do in each of these strata, right? We're going to conduct a simple random sample on each of them separately. And the size of your random sample is proportional to the stratum size. So just like before, what did we say? There's 1,100 undergrads. If I want to select a sample of 12, I'm going to pick 11 as undergrads. I'm going to pick 1 who are grad students. You might ask, how did I pick 12? How do I determine the total number of people to sample? Also something we don't talk a ton about in Data 100, but you have to think about how many people can you pay for? How many people do you have time for? How many people do you actually need, right? I might not need that many to get a representative answer. So choosing your total sample size is also kind of a hidden problem in the background here. Okay. So benefits of stratified random sampling. Guaranteed proportional representation. We talked about this. Reduced chance error. Also talked about this. You're much less likely to get an unrepresentative sample. What are the limitations? Because what did I say earlier? Stratified random sampling is strictly better than simple random sample. It's always just as good or better. Why wouldn't you ever stratify? It adds a layer of complexity. It's an extra couple lines of code. That's something to think about. That can be screwed up. I've done stratified random sampling before, and it got screwed up. When you have a lot of these strata and there's multiple dimensions of it, you can mess things up. Something to think about. It shouldn't keep you from doing it, right? But you got to think carefully. If your strata are already really big, you really don't need to do this. If the class was half grad students and half undergrads, and there were 1,200 people in the class, we'd probably get, pretty close to 50-50 represented, 50-50 of each in like a large enough sample. And a sample of only 12, there's maybe a little bit more chance error, and stratified random sampling makes sense. But if we were to sample, let's say, 200 students from the class, there isn't really a huge benefit from stratified random sampling. But you can see it's minimal chance error reduction. It still is chance error reduction, right? It adds a layer of complexity, but if you code it correctly, you're fine. It's strictly better than simple random sampling. So it's always something to sort of keep in your back pocket to make your sample better. Okay? The other limitation is that if you don't know about the population, you can't do it. If you don't know the number of undergrads and the number of grad students in the class, there's no way to actually stratify based on whether you're an undergrad or a grad student. Okay? But if you know that information, then stratified random sampling is typically a good idea. Okay? All right, so why did I teach you stratified random sampling? Very common in industry. but it's also going to enable us to do something kind of interesting. So let's talk about that to wrap up today. How are we doing on time? Oh, we're doing great. Okay. So coming back to this slide. If you can randomize, that's the best. But very often we can't. Very often we can't randomize. And so I don't want to pretend like if you can't get a random sample that you just can't use your data in any way. Because very often in industry, almost more often, we can't do a random sample. We can't actually random sample. So what do we do? Okay. So non-representative samples are quite common. Customer surveys, super common. Not everyone responds or provides their contact information. Election polling. Back in the day, you'd call a bunch of people, they'd actually pick up their phone. No one does now. No one picks up their phone. Clinical trials, only the people who are willing to take the risk of taking your drug are going to show up for that pay, right? Maybe they don't look like the rest of the population. So non-representative samples are everywhere, but we can still use them. They're still valuable. We just have to be careful. So what can we do? Let me give you another example that's related to what we talked about. So again, Data 100 enrolled students, 100 are grad students, 1,100 are undergraduates, roughly. Let's say that there are 20 Data 100 students in a room, my office hours, okay? On a good day, 20 Data 100 students in a room. It's a non-representative sample. People who are willing to show up to my office hours and listen to me talk, even more than lecture, okay? Let's say there's 10 grad students and 10 undergrads in my office hours. 10 grad students, 10 undergrads, not drawn to scale here. Okay, 20 students, half are grad students, half are undergrads. I ask them how they're enjoying Data 100 this week. 9 out of the 10 grad students are enjoying Data 100 this week. 5 out of the 10 undergrads are enjoying Data 100 this week. Based on just those 20 students, what do you think feelings about the class are overall? What's your best guess of the percentage of all Data 100 students who are enjoying Data 100 this week? So again, 20 students in my office hours, half of them are grad students, half are undergrads. You know the breakdown in the population. You figured out whether or not they like the class this week. What do we think is happening here? What is your guess? Talk with your neighbor. What's going on here? You can defend your reasoning. Make sure you can defend your reasoning here. You might have like a gut instinct. Make sure you can defend that gut instinct, or try to. Okay, why don't you throw in an answer here? Go with your gut if you don't know what sounds like it would make sense. So a very small fraction of the class are grad students. A very large fraction of the class are undergrads, but we have an even split in office hours. Anybody want to share their reasoning for what they picked and why they think before we look at the answers here? Anybody in the about 70% category want to share their reasoning here? Yeah, go ahead, go ahead. Okay, okay. Oh, great. So forget any of like the mathematics here. The idea here is people who are coming to office hours probably like the class. And so everyone else probably doesn't like the class as much. Yeah. And it looks like people in that room, 70%, right? We have 5 out of 10 undergrads, 9 out of 10 grad students. So that averages out to 14 over totals, 14 out of 20, 7 out of 10. So 70% of the room likes the class. Forgetting everything about sampling, just look at the rest of the class. They probably don't like it as much. Good, so less than 70. Other reasoning here. Yes?
70%.
Yeah.
25. If you look at undergrad, only 50%
Uh-huh.
in 25. And since undergrad has larger population in the class in general, so it will bring the percentage down.
Okay, so this is another good answer here. So there's 10 undergrads in office hours, so half are undergrads in office hours, and more of the class are undergrads, the rest of the class, the total class, right? And 5 out of 10 of those undergrads are enjoying the class. And so that 50% is going to bring the overall average down compared to the 90% of grad students. It's not going to be an even split so that it's 70%. It's going to bring that average down. What's the hidden assumption behind that answer? There's a giant assumption behind that answer. Go ahead. Good. This whole answer relies on the assumption that the undergrads in the room are representative of all of the undergrads in the class, and all of the grad students in the room are representative of all the grad students in the class. Do you believe that assumption? I don't. I don't, right? So mathematically, I think an answer of less than 70 makes sense given that assumption. I think the initial reasoning we heard also makes sense given who tends to show up to office hours. And then the last thing is sort of related to that first comment that these aren't necessarily representative of anybody, right? So we can't really say anything. I think less than 70 is a good guess here, but keep in mind how many assumptions you're sitting on top of with less than 70. You're sitting on top of a lot of assumptions. The first one about representativeness isn't quite there. Mathematically, though, let's say we do assume that they're representative. If we assume that the 10 grad students are representative and the 10 undergrads are representative of all 1,100 undergrads, big assumption, then what we can do is overweight the opinions of the undergraduates. And so how do we actually mathematically write out overweighting the opinions of the undergrads? Well, if 1,100 out of 1,200 students in the class are undergraduates, I'm going to give 11 over 12 of the weight to the undergraduate opinion, and I'm going to give 1 over 12 of the weight to the graduate opinion. So how do I write this mathematically? I take 9 over 10, so 9 out of 10 graduate students are enjoying the class this week. In my office hour sample, there are 100 grad students out of 1,200 in the class. So I'm weighting the response. I'm weighting the response with a weight that's equal to the size of the cell in the population. Before we called it a strata. Now I'm calling it a cell. You'll see why in a sec. And then in the second case, 5 out of 10 are enjoying data 100 this week. And I'm weighting that by the 1,100. And I end up with something much closer to 50%. Much closer to 50%. Remember that the undergrad said 50%, the grad student said 90%, the average is 70%. But if I weight the average, it gets pulled more towards 50%. Okay? But again, it's sitting on this huge assumption. And so there's this thing that I want to teach you about, usually doesn't come up a lot in undergrad classes, called post-stratification. We learned about stratified random sampling before. Now we're talking about post-stratification. After the sampling and after we get our results, we're going to use knowledge about the population to re-weight our responses. We're going to re-weight the results based on our knowledge of the underlying population. If I don't know about the underlying population, I can't do this. But very often we do know about the underlying population, like with voters. We know what the American electorate looks like in terms of race, gender, age, income, all this other stuff. We can take advantage of this to reweight our polls. If you ever hear about a reweighted poll, that's what they're doing, post-stratification, okay? So let me give you a more rigorous definition. You're going to divide your sample and population into distinct cells. These are like strata from before. So we divide them into cells. So for example, undergrad versus grad. In the actual class with 1,200 students, I'm going to have undergrad and grad. In my sample, I'm going to have undergrad and grad. I've sampled in some way. I'm going to calculate the overall response in each sample cell, each sample cell. So in each of the groups in my office hours, I figure out what percentage of them like data 100. And then I'm going to use knowledge about the population to reweight. This is exactly what we just did on the previous slide. We're going to reweight our responses, or weight our responses, by the size of the corresponding population cell. In these cells, in this case, we have 2 cells. But you could have a situation where you have, again, 2 by 2 grid, undergrad, grad, STEM, not STEM. You could have a 3 by 3 grid, undergrad, grad, STEM, non-STEM, gender spectrum. You can have a 4-dimensional grid. You can have cells that go deep, 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 deep. How do you compute those cells? Group by in pandas, count things up, right? That's going to come in handy. Okay, what are the assumptions of post-stratification? We figured out all of these earlier. First of all, we actually know something about the population. We have to know that the population cell sizes are accurate. If we're using census data, it's a pretty good sense that we're doing things pretty accurately. One of the great things the census is useful for is post-stratification. And then each sample cell is representative. This is like the giant assumption, the giant assumption behind post-stratification. But it doesn't have to be perfect. And I'm going to show you and try to convince you of that in just a second here. So what's an example of post-stratification out in the real world? Let's think about political polling. So what are some cells we could use instead of undergrad and grad? Look at that first bullet. Instead of undergrad and grad, let's change to US state of residence and political party that you're affiliated with. Okay. Let's calculate the overall response in each sample cell. How many people in each of those groups is going to vote for a particular candidate, and then reweight by the population sizes, or the population cell sizes, right, which come from the census. Let's go back to the Literary Digest poll. So there's a 1936 Literary Digest poll that was conducted, and everybody likes to say, oh, look how bad their poll was, but you could still do a lot of damage with their quote-unquote bad poll. It's pretty amazing what they pulled off, asking so many people and recording all of it. So we can see in the Literary Digest poll, these are the actual counts of people who said they would vote for Roosevelt or Landon from each state. This is a list with 48 states. Hawaii and Alaska had not yet been admitted yet. Okay, the 1936 Literary Digest poll. And then later on in the actual election, something happened. But we don't know. The sample in this case is the Literary Digest poll. The population that we would want to work with are the actual votes from the 1936 election. We don't know the actual votes in the 1936 election. From the perspective of the Literary Digest, that's in the future. And we can't tell the future. That was the whole point of this poll. So then what could we do? Well, let's go back to the 1932 Literary Digest poll. Here is the results from the 1936 Literary Digest poll that somebody by hand tabulated for each of the states. But notice what's going on here. Sorry, it's a little hard to read. On the left here, we have each of the states. Okay, the first one is Alabama, not Alaska. What we have are the number of electoral votes from that state, which is like a fixed number in the United States, right? That's if you want to see who's going to win the Electoral College. Then what we see, Landon in 1936, what was the total number of people who said they would vote for Landon from Alabama in their poll? 3,060. But they also collected some other information. They also asked the voter, how did you vote in the 1932 election? Did you vote for the Republican? Hoover, I think, ran again in 1932. Did you vote for the Democrat? Roosevelt? Did you vote for the socialist? Others? Did you not vote? Or some other candidate? We really care about those two columns. The other columns are going to be pretty small. Okay. So we have something kind of interesting here. In addition to how they intended to vote in 1936, we saw also how they actually voted in 1932. From the perspective of Literary Digest, we know the 1932 election results. So why don't we go back and why don't we say this? Here are the reported 1932 votes from the 1936 Literary Digest poll. So same exact voters, how did they vote in 1932? Presumably somewhat similarly to how they voted in 1936. But we actually know, assuming that they were truthful, how they voted in 1932. We know from the perspective of Literary Digest the actual 1932 election results. Follow me here? We know how people voted in 1932 who were in the poll, the 1936 poll. So we're in the 1936 poll, but we're thinking about their 1932 votes. We know the actual 1932 votes based on just election results that are published. So why don't we do this? Why don't we make some comparisons here? We'll go with Wyoming. In Wyoming, there were 33 times more Democrats voting for the Democrat in the actual election than in the poll. And there were 19 times more Republicans voting in the election than in the poll. Why are these numbers different? What's the reasoning here? Just to make sure people are following here. Why are those two numbers, 33 and 19, different? Why does that make sense or not make sense? What do we think? Why would that 33 be bigger than the 19? Yes. There's bias in the sampling method. Do you want to say more? Does anyone else want to add on to that? How does the bias in the sampling method lead us to have two different numbers? Go ahead. Good. So let me repeat what you said, rephrase it. So the way we polled tended to grab people who were wealthier. And so more people in our poll will tend to be Republican, just in the people we're actually sampling. And so because of that, if there's more people in our poll who are Republican, then sort of by definition, there's going to be fewer people in the actual electorate who are Republican, because we're pulling so many more of them. Democrats are going to be underrepresented in our poll. And so in order to move from our sample of Democrats to the actual number of Democrats, we need to inflate by a higher factor. We now have information that tells us how much more or less we need to inflate the Democrat or Republican votes from the Literary Digest poll in order to get to the actual vote totals. So this is telling us essentially take the Wyoming results, multiply them by 19 for the Republicans to get an estimate for the number of Republican votes, multiply the Democrats by 33 to get an estimate for the Democrat votes for the year 1932. What if we make the assumption that those weights are going to be similar? That the biases that the Literary Digest poll had in 1932 are similar to the biases in 1936? Those are probably pretty similar biases. So why don't I just use these numbers to reinflate the poll from 1936? Let's try that. I'm going to take my 1936 polling results and let's say we're in Wyoming now. So Wyoming's at like the very bottom of this thing. Let's say we have the weights for Alaska. I'm going to take my Republican and my Democrat polling numbers from 1936 and multiply them by the corresponding weights that I calculated from the 1932 election. And let me see if I have enough time to show you the demo real quick. Can we do a 3-minute demo? I think we can. And let's see what happens. And we have to wait for it to restart. Does this actually fix the poll? Also, post-stratification was invented before 1936, and Literary Digest was aware of post-stratification. They asked them later why they didn't do this, and I'll talk about that in a sec. But let's go through this real quick, super quick. I'm going to import here. Okay, we're going to talk about the Literary Digest poll. And all that I have imported is exactly the same data that I just showed you, that big table. Okay, the Literary Digest summary data with all of the electoral votes, all of the people who actually voted Democrat in 1936, how many people in Literary Digest said they would vote that way. Okay, so what we're going to do is we're going to post-stratify. I'm going through this quickly. I recommend going through on your own. All of that text is describing exactly what we just talked about. But what we're going to do is we're going to compute the reweighting factor for Democrats and Republicans for every state by taking the actual number of votes from 1932 and dividing by the number of Literary Digest polls from 1932. And so I'm going to get a Democratic and Republican reweight factor for each state. Notice the Republican reweight factors tend to be smaller. I'm then going to take the polling results from 1936 and multiply by that reweighting factor. And then I'm going to calculate the predicted vote. The Literary Digest raw results said that 43% would vote for Roosevelt. If we reweight using a method that was available to them and pretty simple, we're now predicting Roosevelt will win. Okay, using just a method we learned in class, no fancy modeling, just proportions. And so we're actually able to use those Literary Digest results to get the correct answer here. And so with the last minute or two here, I just want to show you how this is pretty powerful. I'm going to skip this plot, but this isn't just valuable in 1936. These are polls conducted on Xbox before 2012, shortly before 2012. And so you can see the kind of crazy skew that we have in the people responding. The dotted lines represent the actual American electorate. The dots represent the Xbox polls. So you can see overwhelmingly identifying as male versus identifying as female, Xbox in 2012. Okay, so we can see there's a mismatch between the actual American electorate in terms of age as well, tends to be a lot younger for Xbox polls. But we can take our Xbox polls and reweight using exactly the same method I just talked about, and what ends up happening, the 2012 election was a little bit before your time, but Obama did very poorly in that first debate. You can see that the polling numbers tended to go down. He recovered in the second debate and did fine in the third debate. The raw Xbox poll is that solid line at the bottom. A famous pollster is this middle line. The actual election result is that dashed horizontal line. And the post-stratified estimate, using the method we just talked about, the little bit of extra magic on it, using the Xbox poll, was much closer to the election result than the actual polling website. Okay, happy to talk more about this on office hours. Thanks, everybody. See you tomorrow.